Today we're going to look at section 4.2, and this is designing studies. So there are two different types of studies. The first one is an observational study. So this observes individuals and measures the variable of interest but does not attempt to influence them. So observational study is exactly what it sounds like. You observe the person or the object or the animal, but you do not attempt to do anything to influence them. So you look at the person or the animal or the object in their natural state, in the way that they normally are. You don't do any treatment to them. You don't tell them to do anything. You just watch them and you measure whatever variable you're looking for. The other one is an experiment. So an experiment deliberately imposes some sort of treatment on the individual to measure their responses. So we have to do something to them. So if I wanted to see how a dog's coat of fur looks after giving them certain foods, then I'm going to do where part of the dogs get one type of food and part of the dogs get another type of food and measure the differences between the two. So I'm imposing a treatment on them. So that's an experiment and observational study. We're going to focus mostly on experiments in this class because we can control experiments much better than we can observational studies, and we want to have the best data possible. So we need to be able to control all the variables that we can. So if our goal is to understand cause and effect, an experiment is the only source that we can use for convincing data. Observational studies do not prove cause and effect. So it's the biggest thing in this class is to know the difference between observational study and experiment. If I am imposing a treatment, that is an experiment. Observational studies often fail to prove anything because of confounding variables, confounding between the explanatory variable and something else. Well-designed experiments take steps to prevent confounding. So confounding occurs when two variables are associated in such a way that their effects on a response variable cannot be distinguished from each other. So if I'm giving someone, let's say that I want to determine if exercise lowers your cholesterol, and I'm just doing an observational study, which means I'm not telling anyone how much exercise they should do, how long they should do it, what type they should do. I'm not giving them any type of guidance. I am just looking at people who exercise and people who don't exercise and just going from that data. Okay, so I'm not doing anything to them. I'm just observing them. There could be confounding because I might not know if the people who exercise have lower cholesterol because of the actual exercise or because of other things. What if the people who exercise also eat a better diet? So maybe that's what's causing their cholesterol to be lower. So their diet could be a confounding variable. It could be something that's causing me to think that it's one thing that's causing the cholesterol to lower, the exercise, when in reality it actually is something else that causes the cholesterol to lower on them. So that's confounding. When we do an experiment, we control for those things. So we would tell the person, you are going to exercise this many minutes a day, doing this type of exercise, you're going to eat this kind of diet. And tell the other person, you're going to eat the same diet, but you're going to exercise a different amount of time or not at all. So we control something when we're doing the experiment. Observational studies, we don't control anything. So there could be other variables that are confounding, other variables that cause us to think that there's a link between what we're looking at and what we want, when in reality it's something else. Okay, so here we're going to look at some of the vocabulary for experiments. This is really important. I told you chapter 4 is really vocab heavy. It is. It has the most vocab out of all of the chapters for the entire school year. And we will use every one of these words pretty much for the rest of the school year. So you need to know them, definitely. Okay, so first one is a treatment. This is a specific condition applied to an individual in an experiment. So a treatment can be anything. It can be a drug that I'm giving them if it's a drug trial. It can be an amount of exercise they're allowed to do. It can be the type of diet they're allowed to eat. It can be anything that I am imposing on the individual, anything that I am telling them that they have to do. Okay, that's a treatment. Okay, experimental units are the smallest collection of individuals in which the treatments are applied. So your experimental units is the smallest component. So if I'm looking at how dog food affects dogs' coats, then each individual dog is an experimental unit. When we're talking about humans, we don't call them experimental units, we call them subjects. You've probably heard that quite a bit, like when you're watching television and they're talking about drug trials, things like that. We call them subjects. So if it's anything else, it's an experimental unit. Humans, we call subjects. Okay, so in laboratory experiments, they often use designs like the one right here in this outline. So we have our experimental units or our subjects, we give them a treatment, and we measure their response. Pretty simple. This works great if they're in a lab where we don't have any confounding variables, where we don't have anything that could be causing any problems, where we can control for every single thing. That's great. But outside of the lab, this usually isn't the best method to use. So outside the lab, a badly designed experiment can yield worthless results because of confounding. So we have to think of better ways to experiment when we're not doing something in a controlled environment. And most things that people do now for scientific studies are not in a controlled environment. Okay, so how can we experiment well to make sure that we don't get issues like confounding? Well, the way we can do this is to make sure that we perform a good experiment in which some of the units receive one treatment and then similar units receive another. So most well-designed experiments compare 2 or more treatments together. Comparison alone isn't enough. If the treatments are given to groups that differ greatly, bias will result. The solution to this problem is random assignment. So just like we randomly wanted to select our people when we were picking our samples, we also want to randomly assign them to treatments as well. So we want to make sure that if I have a group of individuals, if I've randomly selected people and I just so happen to have 50 males and 50 females in a group, I want to make sure that I'm mixing up males and females into both treatments. I don't want to accidentally put all the males in one group and all the females in another, or purposely do that, because we're trying to randomly assign them. So we definitely want to randomly assign the treatments. So in an experiment, random assignment means that experimental units are assigned to the treatments using a random chance process. It's very similar to sampling, but this time we already have our sample. Now we're taking our sample, we're numbering our sample, and randomly assigning them to the treatments. So here are some principles of experimental design. We just talked about comparison. So this is use a design that compares 2 or more treatments. Random assignment, we talked about that. Use chance to assign the experimental units to the treatment. Doing so helps create a roughly equivalent groups. We want the groups to be as equal as possible. So if it's a good mixture of male and female in one group, we want a good mixture of male and female in the other. We need a control. So keep other variables that might affect the response for the same for all groups. So for example, in my cholesterol problem, if I want to know if exercise causes a difference in cholesterol, then I have to control for everything else that my subjects might be doing. I have to control for their diet. I have to control for any medication that they're taking. I have to control for with a type of exercise they're doing, how long they're doing their exercise. All of that has to be controlled for. That way I know that the only difference between my 2 groups is that one does this kind of exercise and one does not. If there's any other differences in my groups, then I don't know if that difference is causing the data that I'm seeing. And I need to be able to replicate it. This is really important. This is not just in statistics, but in any experiment, psychology, biology, anything. You have to be able to replicate it. So you need to have enough experimental units in each group so that any differences in the effects of the treatments can be distinguished from just chance. So Having a group of 2 and a group of 2 isn't necessarily the best. We need to have enough experimental units in each group to be able to see a replication of it. So, and we'll talk later about how big a sample should be and things like that, and how big your experimental unit should be. But we need to be able to replicate the data. So now we're going to talk about completely randomized designs. So in a completely randomized design, the treatments are assigned to all experimental units completely by chance. Some experiments may include a control group that receives an inactive treatment or an existing baseline treatment. So if I wanted to test dogs' coats, how shiny and soft their coats were after getting a new type of dog food, then I probably would have one group of dogs get the new dog food. That's my treatment group. And then I would have a control group of dogs who just got the original dog food that they normally eat. So they get the control, which is the original, the existing baseline treatment. A lot of times if they do like cancer treatments, new cancer drugs, they will measure them versus chemotherapy. And chemotherapy would be the existing baseline treatment. That would be the one that they know how the side effects are going to look, how it's going to come out. They already have existing data on that. Now they're comparing it to the new treatment. Sometimes they give an inactive treatment. So, for example, if you're doing a study on migraines and you're trying to see if a new migraine medication reduces your migraines, then they might give one group the migraine drug and another group a placebo. And a placebo is just like a sugar pill. It doesn't do anything to you. It doesn't give you anything. There's no benefits to it, no side effects to it. So they just give that so that the person thinks that they're getting the drug, but in reality, they're not. So here's just a diagram. Make sure that you draw this on your notes. So we start with our experimental units and we randomly assign them. So here in my diagram, I had my random assignment for group 1 and group 2. Group 1 is going to get treatment 1, group 2 is going to get treatment 2, and then I compare the results to each other. This is just a completely randomized design. Every experimental unit is just randomly assigned to one of the two groups. So in an experiment, what can go wrong? The logic of a randomized comparative experiment depends on your ability to treat all of the subjects in the same in every way except for the actual treatment. Good experiments, therefore, require close attention to details to ensure that all subjects are really treated identically. So we just talked about a placebo. So response to that placebo is called the placebo effect. So if I'm giving them a sugar pill that has no medical benefits at all, but they think that their migraines are getting better, that's called the placebo effect. Their mind is making them think that the drug is doing something when in reality the drug doesn't do anything. It's just a sugar pill. That's a placebo effect. This is very real. It's very evident in a lot of studies. It's kind of that whole mind over matter thing. If you think that something is going to work, and it does, that's the placebo effect, even if it has no real value whatsoever. In a double-blind experiment, neither the subject nor those who interact with them and measure the response know which treatment they're receiving. This is important. So blinding means that if you're just blinding one way, that means that the person receiving the drug doesn't know. So if I have two groups of patients with migraines, one group doesn't know if they're getting the placebo or the real drug. They don't know. They just know that they're getting a pill. It could be the placebo, it could be the drug, but they don't know. That's blinding. Double blinding is if the subjects don't know and the experimenter doesn't know. So the person who's actually physically handing them their drugs doesn't know if it's the real or the fake. The reason for this is because if you are a person who is giving drugs to someone and you know that they have severe, horrible migraines that make them sick, they're debilitating, they can't go to work, they're very painful, and you know that you're giving them the sugar pill, human nature makes us want to treat them differently. You feel bad for them that they're sick, that they don't feel well. You know that the sugar pill has no real medication to help them, and that you're giving them something that's going to do absolutely nothing for them. So you're more likely to treat them differently, which could cause them to react differently to the drugs. So because of this, they make it so that the person who interacts with the patient, so the nurse that hands them the drugs, doesn't know which one they're giving them, so that they can't have any emotional or different interactions with the patients. That way the patients don't have a clue which one they have, and their data is going to be a lot more sound. Okay, in an experiment, researchers usually hope to see a difference in their responses so large that it's unlikely to happen just because of chance. So we want to see a huge difference. That's kind of the goal. Like, I want to see that my patients who got the actual migraine medication had way less symptoms than the patients who got the placebo. I mean, we know that the placebo group is going to improve a little bit because of the placebo effect, but we want the difference between the two groups to be so large that we can go to someone and say, this couldn't have just happened by chance. This happened because my drug works. So we use the laws of probability, which describe chance behavior, to learn whether the treatment effects are larger than we would expect if we just saw it by chance. If they are larger than what we would expect by chance, we call them statistically significant. Okay, so that's your next word. An observed effect so large that it would rarely occur by chance. So that's statistically significant. Doesn't mean that it couldn't happen by chance. Everything is possible, but it's very unlikely to happen. A statistically significant association in data from a well-designed experiment does imply causation, and this is what we want. If we can control our experiment and design it very well, and we can randomly pick our people and randomly assign them to the treatments and make sure that both treatment groups are the same, and make sure that we control for all the confounding variables, and we can prove that it's statistically significant data, we have done everything that we can do to imply causation. To say that, yes, my migraine medication makes their migraines better, period. So, completely randomized designs are the simplest statistical designs. But just like with sampling, how we had SRSs, which were the simplest type, they're not always the best. So just like with SRSs, we needed to stratify them sometimes, split them up into characteristics to guarantee that we got someone from each group. We can do the same thing for experiments, but we call it blocking when we get to experiments. We block them based on strata, just like we do when we stratify. So if I go and I select my sample, I pick my random 100 people, and then I want to stratify them based on a characteristic. So here in our example, and you're going to kind of sketch this visual as well on your notes. There's a little space for you to do that. So here we have 10 volunteers. We start with 10 volunteers. Then we're going to assign them to blocks. This is not random. We are picking something about these people and separating them into groups. So we looked at our 10 volunteers and we saw that 4 of them are smartphone users and 6 of them are not. So we took our 10 and we put the 4 that were smartphone users in one group and the 6 that were non-smartphone users in another group. Okay, so there's no randomization being done yet, except for when we, well, actually these were volunteers, so they weren't even randomly selected either. There's no random selection done so far. Once we've separated them based on smartphone users and non-smartphone users, that's when we use the random assignment. So then we take our 4 smartphone users and we randomly assign 2 of them to keyboard A and 2 of them to keyboard B. We do the same thing with our non-smartphone users. Take our 6, put 3 with keyboard A and randomly assign 3 with keyboard B. Then for our smartphone users at the top, we compare keyboard A and B together. Do the same thing for the non-smartphone. So we compare A and B for non-smartphone people, their typing speed, and then we compare both of those together. So what we've done is we're able to look and see, is the difference really that one keyboard is better than the other for everyone? not just for people who are good with smartphones, but everyone, even those who are not, even those who've never used a smartphone. So we're taking into account that maybe with smartphone users, keyboard A is better, but with non-smartphone users, keyboard B is better. So it helps us look to see that it's not just about the keyboards themselves, but also about who's using it. So that's why we would do blocking in this kind of situation. So a block is a group of experimental units that are known before the experiment to be similar in some way. So we knew before we started randomly assigning people that some of them had smartphones and some of them didn't. So we used that to our advantage. It's very similar to stratifying, but be careful, it is not stratification. Stratifying is only when you're sampling your original group of people from your population. That's stratification. This is blocking. This is after we already have our people for our sample, we block them into groups. Okay, it's a different type of thing. It's very similar, but they're not the same. You have to know the verbiage of those. A randomized block design, which is what you see up there, that's the diagram, is the random assignment of experimental units to treatments that's carried out separately within each block. So we had our smartphone users, they had their own treatments assigned to them, and then non-smartphone, they had their treatments assigned to them. So we looked at a basic blocked design, randomized block design in the last slide. Another common type of randomized block designs for comparing two treatments is a matched pairs design. So the idea is to create blocks by matching pairs of similar experimental units. So a matched pairs design is a randomized block experiment in which each block consists of a matching pair of similar experimental units. Chance is then used to determine which unit in each pair gets the treatment. Sometimes a pair in a matched pairs design consists of a single unit that receives both treatments. So matched pairs can be two different things. It can be one person who receives two treatments. So there's one like really popular or really well-known stats question from an AP exam where they talk about shoes and waterproofing boots. And they have each person wears one boot that has the waterproofing and one boot that doesn't. And then they have them wear it for 3 months and then they test how the boots look at the end. So each person gets both treatments. Each person has a boot that is waterproofed and a boot that isn't. So that would be a matched pairs design. The other way is when you make blocks that are similar to each other, but you give each block, one person gets one treatment and one gets the other. So maybe if we are testing a shampoo and we want to know how it works on different hair colors, we might take 2 people who are blonde, 2 people who are redheaded, and 2 people who are brunette, block them together. So the 2 blondes go together, the 2 brunettes go together, the 2 redheads go together. And then in each block, we randomly choose who's going to get the shampoo and who's going to get the old shampoo. Okay, so we give one of them the new, one of them the old. In the brunette, we do the same thing. One the old, one the new, and then the redhead, one the old, one the new. And then we compare them. So we've matched the hair colors together, but they've each gotten a separate treatment within the group.